Section 5.4 Inner product space. An inner product space is a vector space V with the inner product. Here is a definition for an inner product. An inner product is the operation on the vector space V. It assigns a real number to each pair of two vectors x, y belongs to V. Now we use this notation to represent the inner product between two vectors x and y. This operation satisfies three conditions. The first condition tells us the inner product of x and itself is always non-negative. And the inner product between x and itself equals 0 if and only if x is a zero vector. The second property is a kind of symmetric property, which means when we calculate the inner product between x and y, that's the same as we start y first and x second. The third property is about the linear combination. So when we look at the linear combination of x and y, say alpha x plus beta y, this vector is inner product with z. We can write it as alpha times the inner product between x and z, and then plus beta times the inner product between y and z. So that sounds like we can work this separately and then pull the scalar alpha to the outside. So these are the three properties for the inner product. When we look at a particular vector space V and check whether or not a given operation is inner product, we have to show these three properties or verify these three properties. For these three properties, let me say the hardest would be check this if and only if part. This sometimes is more complicated than the second and the third property. All right, let's take a look at example 1. Example 1 here, the vector space is Rn. In this case, we define the inner product between x and y by the transpose of x times y. This essentially is a scalar product. It's a scalar product in Rn. We studied in section 5.1. Now for this, we know the three properties are true for this inner product. So in this way, we can say inner product essentially is a kind of extension from the scalar product in Rn. Example 2. In this case, we still take V is equal to Rn. We assume W1, W2 to Wn are positive constants. Then we define the operation between two vectors in Rn in this way. Now this is a summation. It's equal to, here we get the summation for wk times xk times yk. Now for this, we can say if all the w case are equal to 1, then this is the same as the inner product. So in this case, we can say this one is a kind of generalization of the scalar product. And somehow you can say the W is a kind of weight, which means we put the weight for each of this component product. And we can easily show this operation is an inner product, which means that is a property in the definition for inner product. Example 3. Here V equals Rm by n. So this means the vector is actually a m by m matrix in this space. In this case, we define the inner product for two m by m matrix A and B in this way. What does this mean? This means we look at the matrix A is entries are Aij, and B is entries we write like Bij. Then for each cell, we make the product for Aij and Bij. Then add all of them together. So here we have double summation. For I goes from 1 to m, j goes from 1 to n. This makes the operation. Now for this operation, we can check the three properties. For example, the inner product of A and itself, that will be equal to Aij times Aij. So this is the square. So that means the inner product of A and itself is equal to summation for Aij squares. So for sure, this is non-negative. And equal to 0, that means all the Aij squares should be 0. So in that case, we should get A is a m by m 0 matrix. So that way we could say the property 1 for the inner product is satisfied. And then if we switch the order for A and B, then that means we switch order for Aij and Bij. That's okay. So in that way, we can say the second property, the symmetric property, also true. The third property means if we replace, for example, A by alpha A1 plus beta A2, both A1 and A2 are m by m matrices, then that sounds like here we should get the alpha times Aij plus beta Cij, and then for that we can get the separation and we can show the third property. So the third property is for Rm by n. Example 4. In this case, the vector space is the set of all continuous functions on the interval from A to B. In this case, we define the operation between two continuous functions on A, B by this integral. Now, let's take a look at whether or not this operation satisfies the three requirements for the inner product. So first of all, we can say if we take G equal to F, then this is the same as we look at integral for the square of fx. Now, f of x is a real function, so that its square is non-negative. Take integral, we should get this integral is greater than 0. Then we need to look at the if and the earlier part. Earlier we said that's the hardest part, actually. So here is a kind of idea. Suppose f and f for the operation equals 0. But there is one point on the interval f of x0 not 0. Then we are going to get a contradiction. So the idea here is this. If this operation between f and f equals 0, but there is a value x0 inside of interval from a to b, its value not 0. Then recall f is a continuous function, so that we can find a subinterval in the interval from a to b. Let's call this subinterval is I. And x0 inside this interval I. Because f of x0 is not there, so we can get a very small neighborhood in the interval from a to b, so that we get f of x squared is greater than or equal to the half of the square of x0. Now this is a property because based on the assumption of continuity for the function fx. Then we can say the integral from a to b for the square of fx should be greater than or equal to the integral of square of fx squared I, which means now we concede a part of the integral from a to b by a subintegral I. Why we got this inequality? Because here we take square. So square, which means here, if we look at the kind of height here, it's non-negative. So that when we replace a big interval from a to b by a subinterval I, then this should be true. And then we replace this square by this square half, because earlier we got this inequality, so we got that. But both the numerator and denominator are constants, so we can move this constant to the front, and then get left is integral over I dx. That should be equal to what? Equal to the length of I. So in this way, we got this value times length of y. This should be greater than 0. Why? Because in the beginning, we assume f of x0 not equal to 0. So this first part is bigger than 0. The length of I is the interval, so that its length is positive. The product, of course, is positive. Both are positive. Product should be positive. this is contradiction. Contradict what? To in the beginning we assume the operation between f and f, or this integral equals 0. This means what? This means for the operation between f and f equals 0 if and only if the function f of x is identical to 0 over the interval from f to b. So here you say to check if and only if part in the first property is relatively invoked. The second property is simple. Consider integral for f of x and gx. We can switch the order. Switch the order, then we can say by the definition that's the operation between g and f. So this is a proof for the second property. The third property is also simple. We consider the operation between alpha f1 plus beta f2 and with g. Then by the definition, we substitute f in the definition by alpha f1x plus beta f2x. And for the integral here, we can separate the summation, and alpha is scalar, so we can move the front. So in this way, we get alpha times this is integral between f1 and g. And by the definition, we can say that's the operation between f1 and g. So we get that. And then the second term, similarly, we get that's the beta times the operation between f2 and g. Now we can say three conditions in the definition of inner product are satisfied. Now we can call this operation is an inner product on this vector space. Example 5. In this case, the vector space is Pn. Recall, Pn is the set of all the polynomials of degree is less than or equal to n minus 1. Now, in this case, we pick up n distinct real numbers x1 to xn, and then define an operation between two polynomials belonging to Pn by this way. So take a look. Px is a polynomial. We take its value as xk, and q is another polynomial. Take its value at xk. Then make this product add together. Now here we have n terms for this kind of sum of production. We want to show this operation is an inner product. Now to do that, we need to verify the three properties in the definition of inner product. So let's start with the first property. The first part of the property 1 is simple, which means we take q equal to p. So in that way, we got the operation between p and itself equal to the summation of squares of pxk. Because p is a real valued polynomial, so that the square for sure is non-negative, and we get this sum of the squares of products here is non-negative. Now we need to show if and early if part, which means we want to show the operation between P and itself equals 0 if and only if P is a 0 polynomial. So if the operation between P and P equals 0, that means this kind of summation here equals 0. But each term is kind of square. So the only possibility is all these squares equals 0. That means pxk equals 0. Now, here we can say pxk equals 0. This x1, x2, xn are different. So that this means the polynomial px has n distinct rows. But the question is, px is a polynomial of degree n minus 1. So the only possibility is just the px must be identical to 0. So in this way, we say the first property for the inner product is true. The second property is simple. We evaluate the operation between P and Q. So by the definition, that's the product of P xk times Q xk. And of course, we can have a change of the order. So we write it down like a Q xk times P of k. By the definition, that's equal to the operation between Q and P. So second property for inner product is true. The third property is also simple. In this case, we substitute the px by alpha times p1x plus beta times p2x. And then by the definition, we get this kind of summation for the product. And for this summation, we can separate them. And then alpha, we can pull to the front, so we get this. And the same thing for the second part. Then look at the definition for the operation. We can say this is the same as the operation between P1 and Q, and times alpha. So we get first term is the same thing for the second term. So in this way, we can say the third property in the definition of inner product is satisfied. Now, because the three properties are satisfied, so that we can call or we can claim this operation is an inner product on the vector space Pn. Now let's take a look at basic properties of inner product spaces. Here we use red ink to give a statement. The results for the scalar product in Rn are generalized to the inner product space, which means what I'm going to say in the following are just a kind of generalization from the scalar product in Rn. So this actually gave us a good idea to review the results in section 5.1 and then do the generalization. This is very important from a simple case to a general case. First of all, we define the length or the normal for a vector x in the vector space. Now we call this is the inner product space because uh, in the vector space, we may not have inner product. Now we already have the inner product, so that in this case, we can define the next or the called norm. We use the similar notation just like what we used for the next in Rn. We call this kind of notation. But in this case, the next is defined by the square root of the inner product of x and itself. Recall, for the first property of inner product, the inner product between x and x itself is non-negative, so that this inner product makes sense. We call this square root of inner product x between x itself is the next of vector x, or the norm of x. Of course, the next here is a kind of term. It may not be like the next in Rn, but here the term we call the next or the norm. For two vectors in the inner product space V, we can define orthogonality. Two vectors x and y are orthogonal if the inner product between x and y equals 0. So this is the same or just extension in Rn. Theorem 5.4.1. The Pythagorean law. If we have x and y are orthogonal, then we have the square of the length of x plus y equal to the square of the length of x plus the square of the length of y. Now, we proved this property in Rn when the inner product is the scalar product. Now, this is generalized to inner product. Here is the simple proof. The square of the length, by definition, that means here we take both sides square, and here we look at x plus x. So x plus y and itself make the inner product that's equal to the square of the length of x plus y. Then for this inner product, we can evaluate this according to the third property for the inner product. So which means for this two terms, we can evaluate the inner product between x and x first, and then x and y, then y and x, then y and y. So we got this form. Now this is operated based on the third property for the inner product. And then because we assume the x and y are orthogonal, then inner product equals 0. So this second term is equal to 0. The third term is also 0 because the y and x we can switch the order. So in this way, we get the second term, third term both equal 0, and then this inner product between x and x equal to the square of the length of x, and the same thing for the last term. So in this way, we proved this law. Example 6. In this case, the vector space V is the set of all continuous functions on the interval from negative pi to pi. In this case, we define the operation between two functions f of x and g of x by this integral. Here, we can show this this operation satisfies the three properties for the inner product. Then we can look at two examples. Say let's pick up or specify f of x is a function identical to 1, and then g of x is equal to x. So these two functions, of course, are continuous on the interval from negative pi to pi. We can say these two functions are orthogonal each other based on the inner product because the inner product between f and g equal to 1 over pi, then this integral from negative pi to pi substitute f of x by 1, g of y by x, then we get x. And this integral equal to 0. So that means the inner product between f and g equals 0. By definition, these two functions are orthogonal. Second example here is we take f of x equal to cosine x, g of x equal to sine x. Then we can say these two functions are orthogonal each other. The reason is their inner product equals 1 over pi times integral from negative pi to pi for cosine x and sine x. You can easily show the antiderivative in this case equal to sine square pi over 2. And we should put 1 over pi in the front. But no matter what, this value equals 0. So in this case, the two functions are orthogonal based on this inner product. The Cauchy-Schwarz inequality. This is the theorem 5.4.2. We consider two vectors in the inner product space V, say x and y. Then the absolute value of inner product between x and y is less than or equal to the product of the length of x and the length of y. This here the symbol is less than or equal to. If we consider equal, then the equal sign holds if and only if x and y are linearly dependent. Now, we proved the Cauchy-Schwarz inequality when V equals Rn. In that kind of case, the inner product is the scalar product. Now we're going to prove this inequality when V is the inner product. We're going to use a different proof. The proof is different from the method in the textbook. We use the same idea we used for the case when V equals Rn. To do this, we are going to assume x is not 0 or y is not 0. Why? If we take a look, for example, if x is 0, then the inner product between 0 and y, that equals 0. Then the right side, the next of x is 0. So in that way, we can say this inequality becomes a equality. So that for sure is true. Similarly, if y is 0 vector, then we get this both sides are 0. So we actually don't need to say more for x or y equals 0 case. Now let's concentrate on the case when x is not 0. In this case, we define a function f of h of z. H of z is a function of z is defined as the square of the next for the vector zx plus y. Now, for this function h of z, we can say h of z takes non-negative value. I'm sorry, this should be h of z, not f of z. And then we can say h of z is a quadratic form or quadratic function of z. Why? We just use the definition h of z equal to the square of the length for zx plus y. That's the same as the inner product between zx plus y and zx plus y. Then we use the third property of inner product to evaluate this inner product. That's the same as z squared times the inner product between x and x, because that should be equal to the inner product between zx and zx. But z and z are both a constant, so we can move to front. So in that way, we get z squared. And then here we have zx and y make inner product. Z is constant, so we can move front. So in that way, we get the z times the inner product between x and y. And then we have y and zx make inner product. Z is the scalar, we can move to front, so that's also the same as inner product between x and y. So in that way, we get the double of z times x, y inner product. Then y and itself make inner product. Then we can say here, inner product of x and itself equals the square of x next. So we get this term. And then the last term here is equal to the square of the next of y, or the norm of y. All right. H of z here is a quadratic form. So this quadratic form just take a non-negative value. In other words, this quadratic form doesn't or just touch the x-axis, the z-axis earlier. So in this case, this quadratic function takes non-negative values if and only if it has no real root or two equal real nodes. Now we know this fact in high school or maybe in middle school, so that the coefficients for the z term, that's 2 times the inner product of x and y, take square minus 4 times the coefficient of z squared, and the constant term should be less than or equal to 0. Now for this, we have 2 squared, that's 4, so 4 for we can divide from the two sides of the inequality. Then move the second term to the right side. Then take square root, we get the the absolute value of inner product between x and y is less than or equal to the product between the length of x and y. Inequality holds if and only if and only if what? If and only if this quadratic form has two equal roots, right? That's the fact we knew in middle school or high school. So that means the equality holds if and only if there is a z such that h of z equals 0. What means h of z equals 0? H of z equals 0 means this square of the inner the square of the length of zx plus y equals 0. That by the first property of inner product, that means zx plus y equals 0. Zx plus y equals 0 means zx plus y 0 means x and y are linearly dependent. The benefit for the coexistence inequality is it gives us a chance to introduce the concept of angle for two vectors in an inner product space V. Because what? Because from this inequality we can say if both x and y are non-zero, then we can divide this inequality both sides by this product. Then we get the absolute value for the quotient of the inner product between x and y over the product of length of x and y, x times the length of y is less than or equal to 1. So in that way, we can say the value is between -1 and 1. We can consider is arc cosine. In that way, gave us chance to introduce concept of angle in an inner product space. So here's the definition. We consider two vectors x and y in the inner product space V. We define the angle here theta by this notation. If either x or y is 0, then the angle we take as 0. If both x and y are non-zero, then the angle theta is defined as the arc cosine of this quotient. Now, based on the coexistence inequality, we know this quotient is between -1 and 1. So that in this way we can define arc cosine for this value. Now, this arc cosine value here is the angle. For this, we can say the angle between x and y is the value between 0 and pi, because arc cosine takes the value from 0 to pi. Consider a particular example. If x and y are orthogonal, then their inner product equals 0. Then we just plug into the definition here. We can say the coefficient for this quotient is numerator is 0, so that the whole value is 0. Arc cosine 0, we know the value is pi over 2. So in that way, we call x and y are orthogonal. So this is just the kind of generalization from elementary geometry. In that case, we say if we have angle is pi 2, then we call x and y are perpendicular. So perpendicular orthogonal uh, similar notation in inner product space and in elementary geometry. All right, let's now consider the question we talk about in Rn. Here you can say we assume V is an inner product space. We consider two vectors x and y in the inner product space. We assume the vector y is non-zero. What we're going to do is we're going to find the scalar alpha and the vector z. Z, of course, is supposed to be a vector in the inner product V. So that x can be written as the summation of a scalar alpha times y over its next, then plus z. Here we require y and z are perpendicular, or y and z are orthogonal to each other. So if we take a look at this decomposition, we can say alpha is scalar, y over the next of y is actually a direction vector. Because what? Because y over its next for this vector is a unit vector, which means its length equal to 1. So this is a generalized question from Rn. To now, V is inner product space. The answer is actually the same as what we had in section 5.1. So we use a similar term, scalar projection of x onto y. Scalar here is alpha. So here the alpha equals the ratio of scalar product of xy over the next of y. Now from this you can say y in the beginning we assume the vector y is non-zero because we should guarantee this denominator is non-zero. And then the vector projection of x onto y equal to alpha times this unity vector. Now, if we substitute alpha by this quotient, then we get this form. The reason is because alpha, the numerator, is the scalar product between x and y. So that's this numerator here. And then we have the next of y here, and also a next of y here. So that means we should have the square of the next of xy. That's the same as the inner product of y and itself. The reason why we write in this way is because we want to show the similarity. So the numerator is the inner product between x and y. The denominator is inner product between y. And then this quotient is a scalar because the inner product between x and y is a real number. The inner product between y and itself is another real number. So this quotient is real number. Then this scalar times vector y, we get a vector. So in this way, we say this is a vector projection. We got the value here is a vector. Then the question is how to show this is true. The idea is similar to what we did in section 5.1. Now, here the treatment is different from method in the textbook. We use the same idea in section 5.1 to give the solution for this question here. You can take a look at the textbook and then compare with the method here. So in this way, you get two methods for the same question. All right. The idea is simple. In this case, we can say the inner product between y and x. Here, x is required to be written as this kind of 4. So take the inner product for x and y, then that's the same as substitute x by alpha times the quotient y over is x plus z. And then this time we need to use the third property for the inner product. We can write this one as move the constant alpha to the front and then evaluate this actually the constant or the scalar is alpha over the negative y. So we can move this part to the front and then evaluate the inner product of y and y. So we get this term. And then z and y. Then we can say the alpha times this is inner product of y and itself. That we can also write it down as a square of the negative y. So we can cancel the 1 next. So in that way, we get alpha times the negative y. Then z and y, they are orthogonal each other. Orthogonal each other means the inner product between z and y equals 0. So in that way, we get the second term here is 0. Then look at the far left and the right. We can both sides divided by the negative y because y is non-zero, so that we can make that kind of division and then we can get alpha. So alpha is equal to the inner product between x and y over the negative y. So in that way, we substitute the alpha here. Then we can get x is the composition like this. Now this part is this. So in that way, we get the solution here. We got a scalar projection of x onto y by alpha, and then vector projection of x onto y at this kind of form. So this part is essentially a generalization from Rn to an inner product space V. All right, this is a new definition. This new definition is called a normed linear space. First of all, we assume V is a vector space. And we say this vector space is a normed linear space if there is a real number here associated to each vector V belongs to the vector space V. Now, this real number satisfies 3 conditions. This symbol is called the norm of V. Now recall earlier we introduced the length or the norm of a vector in the inner product space. So now you can say the term. You can say the term. Now for this, we have three conditions. The first condition is the norm of V. Sorry, this should be above the case V. The norm of the vector V should be all the time non-negative. So that's just like next. And this norm equals 0 if and only if the vector V is the zero vector. The second property is if we consider alpha times x, for this vector is norm equals the alpha value take opposite value, then times the norm of x. This is for all scalar alpha. Now here we have to be careful. This sounds like we can move the scalar alpha to the front of the norm. But when we do this, we have to be careful the scalar when it moves from the norm here, we should take a non-negative value or take the opposite value, so make it non-negative. Otherwise, we could get trouble because what? In the first condition, we assume all the norms are non-negative. If here we don't take opposite value, then we could get a negative value. So that's why here we take the non-negative value for the opposite alpha. The third property is called the triangle inequality. That says this: if we consider the norm of x plus w, then this norm should be less than or equal to the norm of v plus the norm of w. If we draw a triangle here, say this here, this vector is vector x, and this vector is vector y. Then we can get the third vector here is x plus y. This is similar in Rn. In this case, look at the arrow. It goes from this point to here, and then y starts from the end point to z. Then x plus y precisely goes from the starting point of x to the end point of y. So that's a geometric version for the three vectors x, y, and x plus y. Now in this case, just like what we knew in middle school or high school, the length of the third side is less than or equal to the length of two other sides summation of the length. So that's a geometric interpretation for the triangle inequality here. So you can say this is a kind of geometric interpretation. When we introduce new notation or new concept, we typically try to look at whether or not it's linked to what we studied earlier. So that's the three properties for a norm to be satisfied. Theorem 5.4.3. In this case, we assume V is an inner product space. Then we take a square root of inner product between V and itself. In this way, we define this operation. Now, this operation actually defines the norm on V. Now, when we read this, we need to be careful because V is the inner product space, so that the inner product V and itself is well defined. Take square root, no problem, because the inner product V and itself non-negative. But here, this symbol or the symbol for the norm should be read as new. This is not this is think about the new, although we define the length or the norm in the inner vector space, inner product space. So what does that mean? That means if we want to show this definition actually gave us the definition for the norm, we have to verify whether or not these three properties are satisfied. Here is a proof. To prove this, we can say the first property is true because what? Because based on this definition, the square root of inner product x and V and V itself is non-negative for sure. And then this inner product equals 0 if and only if V is 0. So the first property for the norm is satisfied. The second property is true because what? Because if we substitute V by alpha x, then we can say we get alpha x and itself make inner product. Alpha we can move out, and another alpha move out, we get alpha squared. Then take a square root of alpha square, we should take opposite value. So in that way, we get alpha opposite value times length of x. So the first two property we show are satisfied. Then we need to verify the third property or triangle inequality. In this case, we consider the square of the length. Sorry, this is not length. The square of this operation for vector v plus w. Then, for this, by the definition here, that should be take a square of this. Then that means we look at the inner product between v and itself. So in this case, it's v plus w and itself. And then we can say that's the same as use the third property for the inner product. So that we should write as inner product between v and itself. So that's the first term. And then v and w and v, they are the same. So we get double of the inner product between v and w. Then w and itself make inner product. Then by Cauchy's inequality, we know this inner product between v and w, if we take opposite value, should be less than or equal to the length of v and the length of w. So we got this. And then here we can say v and itself make inner product that's equal to the length of v, and the same thing for the third term. And in this way, we got this is actually a complete square. The complete square that's actually equal to this. Then both sides we take a square root. We got the triangle inequality satisfied. After we check this three property, we say all the properties satisfied. Now we can say this kind of definition actually defines a norm on the inner product space V. So for this kind of question, what we need to do is just look at the definition or property one by one to show each one is satisfied. Here is an example in Rn. In this case, we take V is Rn, and then we define this kind of rotation for a vector in Rn. What we did this time is for each component of vector V, we just take its opposite value. If we, for each here, for each component we take opposite value. Then what we are going to do is we are going to verify the three properties for the norm. Once we've done that, then we can claim here we got a normed linear space Rn. The first two properties we can easily verify. For example, the first property is for this sum of opposite values for components should be always non-negative. And this summation equals 0 means all this opposite value should be equal to 0. That means all the vk equal 0. Equal 0 means v should be a 0 vector. So in that way, we can say the first property for the norm is satisfied. Then the second property is if we look at the alpha x, then that means we need to have the summation for the opposite value of alpha xk. Move alpha to the outside of opposite value, we should keep the opposite value for the alpha. So in that way, we get the right side should be the opposite value of alpha times the opposite value of vk. So from that, we can say the second property of norm is also true. Now let's concentrate on the third property. That's the triangle equality. In this case, take a look here. We put a subscript here, 1 here. That means what? That means here we just take the power is 1. Then, in this case, by the definition, we can say v plus w here for the definition equal to the summation for the opposite value of vk plus wk. Then the sum take opposite value we know is less than or equal to we take opposite value separately. So look at this. Then by the definition we can say the first part is actually by the definition that's v and then the second one is for the w. Put that together, that means the third property or the triangle equality is checked. Based on the three properties now, we can call this symbol here defines a norm. And now, based on this norm, Rn is a normed linear space. We call this is the L1 norm. Why is it called the L1 norm? It's because here we can look at the general case. Here is the general case. The general case is like what? The general case is like this. We consider P is a constant. The constant is greater than or equal to 1. Then for a vector in Rn, we calculated the absolute value of the component. So Vk takes the absolute value, then make it to the power P. We have to take this absolute value first because Vk could be a negative. When in that case, if P, for example, is a number like 1.25, then we could get a kind of problem, take the power. So in that way, we have to take the absolute value first and then take the power P. After we done the summation for this, then to the outside, we take a larger power, that's 1 over P. If P is 1, we can say when P is 1, then we got this is the same as example 8. Another special case is P is 2. When P is 2, we can say that should be Vk absolute value squared. So that's the same as Vk squared. And then to the outside, we have 1 over 2. So in that way, we can say that's actually it's for the scalar product space R. So from this, we can say y is called L1 is because the P here equals 1. And then this the next in or the next is actually here is for P is 2. So here is a more general case for the example of L1 norm. Here is LP norm. All right, that's all for today.